Important family of sequences are the so-called recursively defined sequences. And in fact, the Fibonacci numbers that I mentioned here, they're a very well-known family that's a very well-known example of a recursively defined sequence. So I'm going to use f sub n to, we don't have to use a sub n. I'm using a capital F sub n here for the Fibonacci's. And so how am I going to define it? F sub 1 is going to be 1. F sub 2 is going to be 1. And F sub n is going to equal F sub n minus 1 plus F sub n minus 2 if n is at least 3. So you take the two previous numbers and you add them together. And that's how you write down the Fibonacci numbers. So it starts off 1, 1. We add the two previous numbers together and we get 2. We add the two previous numbers together and get 3. We add 2 plus 3 and get 5. We add 3 plus 5 and get 8. 5 plus 8 and to get 13, 21, 34, 55, 89, 144, so on and so forth. So this is a very common way, and we will certainly do this throughout this chapter. We will sometimes define sequences recursively. Now there is an explicit formula. I should be clear here. There is an explicit formula for the Fibonacci numbers, but it is easier for us, and there's nothing wrong with examining the Fibonacci's using their definition recursively. Okay, here is another example just to work out. A sub 1 is equal to 1. A sub n is equal to 1/2 times a sub n minus 1 plus 2 divided by a sub n minus 1. Let's write out the first several terms of the sequence. So a sub 2 is going to be 1/2 times a sub 1 plus 2 divided by a sub 1. So that's going to be 1/2 times 1 plus 2 divided by 1. So that's 1/2 times 3. So that's 3/2. A sub 3 is 1/2 a sub 2. All right, that's 1.5 plus 2 divided by 1.5. And when you crunch that out, you get 17/12. And a sub 4 is equal to 1/2 times 17/12 plus 2 divided by 17/12. And when you crunch that out, you get 577 divided by 408. So in this case, we can calculate as many terms as we want to. Obviously, the calculations are going to get a bit messier. Past this, we could probably do this by hand. Pretty soon, I'm going to feel a little bit awkward doing these calculations by hand, which is reasonable. But recursive definitions, we can calculate out as many terms we want. To be very easy to do this with a computer. Computers, a lot of the things that they do are very much using a recursive mindset. But there's something else that I want us to look at here. And so the thing I want us to look at is, so we start off, our first term was 1. The second term, 3.5, is 1.5. The third term is about 1.4167. And the fourth term is about 1.414216. So there's a couple things you should notice here. So 1, 1.5, 1.4167, 1.414216. So note here that these two numbers are very close together. And so basically what's going on, you might think, and it would be a reasonable thing to think, that these numbers, as we keep going, are going to get closer and closer to some value here that's roughly 1.414216. And not only that, but if you're really clever, you might notice that, this number might look a little bit familiar. This number is approximately the square root of 2. And so as it turns out, if we keep computing more and more terms of our sequence, we keep getting closer to square root 2. And so informally, we'll make this more precise. This isn't exactly, I'm phrasing it a little bit inexactly, but what this is going to tell us is that the limit of this sequence is the square root of 2. So here comes our big definition here for this section. Now we care about not just about sequences, but the limits of our sequences. So we'll say that a sequence a sub n converges to the limit L, which the notation for that, we can write limit as n goes to infinity of a sub n is equal to L, or we can just write a goes to, that should be an L there. If for every epsilon greater than 0, there is an m such that the absolute value a sub n minus L is less than epsilon for all n greater than m. So this is harkening back to limit stuff. Some points here. If no limit exists, we say the sequence diverges. If the terms increase without bound, we can say that a sub n diverges to infinity. But more importantly, going back to this convergence, this says we will eventually get arbitrarily close to the cutoff value. So to the value of the limit, that's what this is saying here. So in the previous one, as it turns out, this recursively defined sequence has limit root 2.